Good morning. Welcome to class. It is Wednesday, April 22nd. At least I think it is. All the days are just kind of blur together by now. Um, so we're going to continue talking about circuits. So the goal is to get through the classwork today. We might have a little bit left over to finish next class. Uh, but yeah, we have that. Today we're going to go through series and parallel circuits, still dealing with simple circuits. Next week we'll be talking about combinations of these circuits, and then the week after that you'll have a review and test, probably the last test of the year. So this is the last big topic. We might have a little bit of time for a little small topic after that. But yeah, just make sure you're looking on Skyward, keep up with everything. If you haven't turned in the Coulomb's law quiz or the waves test, get that in. Or if you still haven't finished the lab, get those in. Just check Skyward for the grades I'm picking up. And all the other assignments, if you haven't finished those, if you work on them, I'm giving you points elsewhere. So even if the grade doesn't appear in Skyward, if you do assignments, you're still going to improve your grade. All right. So last class we introduced a few things. So again, make sure you're looking at the classwork, not the homework. They look very similar at the top. So we introduced a new equation, Ohm's law, voltage equals current times resistance, and these are spelled out right here. So again, voltage is like the push that's pushing the charges through the wire. So the battery pushes the charges through the wire. This is what makes things go. Current is the moving charge through the wire. Again, it's the electrons moving through the wire. So how many electrons flow through the wire per second? And we have a whole other equation for this. Current is the amount of charge flowing through a wire per second, per time. And then lastly, we have resistance. So resistance tries to slow down that current through the wire. And resistors are going to be the useful objects in a circuit. So a lot of times it could be something like a light bulb, or if you plug in your phone to charge it, your phone is a resistor. But yeah, resistors are useful devices, the things that were actually getting used. Units are ohms, and this is the only weird one. We use a capital omega because if we use an O, it would look like we're using a zero. Then we have an equation for power. So we still have our old power as the amount of work per time or change in energy per time. But we can also get electrical power, would be current times voltage. And today we're going to get into these two equations for a series and a parallel circuit. So we're going to start off today looking at this second problem right here, this circuit right here. So I have a 10-volt source, and then we're sending current through a 100 ohm, 500 ohm, and 400 ohm resistor. So we're dealing with circuits with multiple resistors. So let's just sketch that out real fast. So we have a 10-volt source, send current through resistor 1, resistor 2, and resistor 3. R1 is 100 ohms, R2 is 500 ohms, and R3 is 400 ohms. All right, so we have the circuit with a lot of different devices in it, and this is the simplest way of connecting things together in series, where you just go through each individual object in a row. So this is a series circuit. Number 2. All right, so the first thing we want to find is our total resistance. So before we just had one resistor, we just had to deal with one resistance. Here we're going to be looking for total resistance. Another word we can use to describe this would be equivalent resistance, so total or equivalent. So we have, actually I think that's not equivalent, something like that, I can't spell. So we have our total resistance. Now, when we're looking at this, let's imagine we're in a grocery store. So I'm in a grocery store, and I have to go through 3 different checkout lines. So when we're here, So I go through this checkout line, they check out my groceries. Then I have to go through this checkout line, they check out my groceries. Then I have to go through this checkout line. How easy is it going to be to leave the store if I have to go through 3 different checkout lines? Easy or hard? Yeah, it's going to be pretty hard. I go through this checkout line, they check all my stuff, I put it in my cart, then I go through this one, they check all my stuff, put it back in the cart. I go through this one, they check all my stuff, and I put it in my cart. So if this was a grocery store, this would be really hard to lead. So we're going to see series circuits are going to have large resistances. So I have to go through this resistor and this resistor and this resistor to get back to my battery. So we're going to see really big resistance here, and that's shown by our total resistance for a series circuit. It's just going to be adding up each individual resistor. And then on your formula chart it says plus ... So we can do this for any amount. If I have 4 resistors, it would be R1 plus R2 plus R3 plus R4, and any amount. We're just adding these all up. Easy shoplift. We'll talk about shoplifting next class. There is actually an analogy for that, so just stay tuned. All right, so we have a 100 ohm resistor and a 500 ohm resistor. So we could think of this as being a person who's really good at checking people out because it's a small resistance to leaving. Yeah, shoplifting. It's a short in the circuit. Then R2, this person is new and they kind of suck at checking people out, so they have a really big resistance. And then this person is a little bit better. They've been there for like a week, so they're a little bit better at checking out your groceries. So you add these up, 100 plus 500, 600 plus 400 is 1,000. So we have a total or equivalent resistance of 1,000 ohms. Or we could also express this in kilo ohms. This would be 1 kilo ohm. Uh, 1,000, not O. Yeah, it would be nice if you could use O. It would just look like 1,000 K0. It would look really weird. All right, so we see that our total resistance is going to be bigger than any of the individual resistors. So resistance total is larger than any individual resistance. Which kind of makes sense because I have this resistor here, my 500 ohm resistor. My total resistance is bigger because I also have to go through these. It makes it harder to get through my circuit. All right, so B wants us to get our total current through the circuit. So we're dealing with our totals. We can look at this whole circuit overall at once. So that's a lot of times how we're going to be starting this out, looking at our entire values before we start looking at values for each individual resistor. So this I can use Ohm's law. So total voltage equals total current times total resistance. I would suggest using these subscripts. We'll see later where I could do voltage across resistor 1 equals current across resistor 1 times resistance of resistor 1. This is just really good for keeping things separate and not kind of confusing yourself. So I'm trying to find the total current through the circuit. So current total, I would just divide resistance over. It's going to be total voltage divided by total resistance. All right, well, I have a 10-volt battery, and I have 1,000 ohms of total resistance. 10 divided by 1,000 is the same as 1 divided by 100, or 0.01 amps. So I have a total current of 0.01 amps. And again, by the way, 1 amp is a pretty large amount of current. It only takes about what is it, like 0.01 to 0.05 amps across the heart to stop it. And then 0.075 amps across the heart will almost certainly kill you. So 1 amp is pretty large. Again, it's hard to actually send that through your body. But yeah, if you're looking at an electrical device and it's talking about something with multiple amps in it or things like that, then I would not mess with it too much, especially if it's in the tens to, yeah, you probably shouldn't have anything in the hundreds of amps in your house unless you're dealing with like the main electrical supply. But yeah, these are not things to play around with. And yeah, it is the current that actually harms you. It's not the voltage. The voltage is just the thing trying to push the charge through your body. It's ultimately how much of that charge actually goes through your body that's actually harmful. All right, so I have the total amount of current through the circuit. C wants me to figure out how much current I get through each resistor. And then this is where we kind of have to go back to what current is. Current is the movement of charged particles and in particular, when we're talking about charged particles, we're talking about electrons. So this is the movement of electrons. So when we're talking about current, we're talking about how many electrons are moving through a point at a given time. So that's where we get our equation, is the amount of charge flowing past a given point in a given time. And then we get to the point where we're talking about electrons. Well, we're not creating electrons or destroying electrons. So we go to this whole, it's a lot of energy to create or destroy electrons. So in a normal circuit, so in a low energy circuit, like everything we see today, unless we're talking about something like a really powerful atomic bomb or a particle accelerator or a black hole, these electrons are not being created or destroyed. So what we have here is that the electrons are getting pushed out, and however many electrons are pushed out are the same amount of electrons that are returning. Yeah, Waxahachie, they were trying to build a particle accelerator there. It was going to be like 4 times the size of a Large Hadron Collider. They dug out much of the tunnels, but they still needed another like 10 to $100 billion to finish it. And unfortunately, the budget got cut in favor of the International Space Station. So yeah, we almost had an absolutely massive particle accelerator near Waxahachie, which is unfortunate. You know, I mean, when you look at the actual like budget of the U.S., you know, like a few tens of billions of dollars, like isn't that huge. But yeah, we almost had the world's largest particle accelerator in Texas. Sad days. Yeah, walking distance from it, that's kind of a vague notion. Walking distance from where? We're talking about a thing that was, I think, going to be like 30 to 40 miles wide. Giant circle. So it depends if you were close to where like the actual like lab was going to, yeah, the actual central base of the lab. Yeah, they built a lot of the thing. They never installed any of the sophisticated equipment there. But yeah, we're not dealing with that. Technically, a particle accelerator, it is a current. You have moving charges, and you can rip apart electrons into the most fundamental units. You can rip it apart into like quarks and gluons and all these random exotic matters. But we're just dealing with nice, simple circuits like this, like a nice, simple AA battery with a nice, simple light bulb. Whenever I plug this in, this is not enough energy to create or destroy the electrons. It does sound fun. I mean, I guess we just have to do with the Large Hadron Collider, which is still, in all rights, pretty fun. It uses up as much energy as a small city does, and when it's being used. So yeah. All right, so electrons aren't being created or destroyed. So I have the same amount of electrons leaving the battery as returning, right? So same number of electrons leave battery as the number of electrons that return to the battery. So if I were to sketch out my circuit again right here, we're going to see I have my total current going out. I send out 0.01 amps here, and that's just a moving charge. Well, the charge isn't being created or destroyed, so I have all 0.01 amps of current going through here. Well, no electrons are getting created or destroyed. 0.01 amps here. And no electrons are created or destroyed, so 0.01 amps here. And then all of that current returns back to the battery. So we're going to see that our current is not changing throughout each of these. Unless there's like a freak event and like a random cosmic ray hits one of these. But yeah, that's not going to hit. That's not going to be any significant amount. So we're going to see in a parallel circuit, in a series circuit, I mean, sorry. So in a series circuit, each resistor gets the full current. So they're not having to share this current. They each get the entire current from the battery. So the current through resistor 1 is going to be the full 0.01 amps. The current through resistor 2 is going to be that full 0.01 amps. And the current through resistor 3 is going to be that full 0.01 amps. And that's just all due to charge not being created or destroyed. All right. Now D wants us to get our voltage drop across each resistor. Now this is going to be a little bit different. So I have 10 volts I'm sending out here. Let's see if each one of these gets the full voltage. Well, I can look at my Ohm's law equation, and a better way of writing this is actually the change in voltage across a resistor is going to be current times resistance. And this is where we're not trying to find the total voltage drop for the entire circuit. I'm trying to find this for each resistor. So the voltage drop across resistor 1 equals a current across resistor 1 times the resistance of resistor 1. All right, so I send 0.01 amps through each resistor, and resistor 1 is a 100 ohm resistance. 0.01 times 100, it's a nice, easy 1 volt. Then I can get my voltage drop across resistor 2. It's going to be the current across resistor 2 times resistance 2. Voltage drop across resistor 3. It's current across resistor 3 times resistance 3. 0.01 amps. 2 is that 500 ohm resistor. And then 3 is the 400 ohm resistor. And it's almost like I chose nice, easy numbers. 500 times 0.01 is 5. And 400 times 0.01 is 4. Voltage drop for 1. Voltage drop for 2. Voltage drop for 3. Now, I sent out 10 volts. This one only gets 1. This gets 5. This gets 4 volts. So they're not each getting that full voltage, but what's special about 1, 5, and 4 compared to 10? 1, 5, and 4 compared to 10? Well, 1 plus 5 plus 4 equals 10. Yeah, I add them all up to get to 10. So what I see here is that the total voltage for the circuit, total voltage for the circuit is the voltage drop across resistor 1 plus the voltage drop across resistor 2 plus the voltage drop across resistor 3. This is a pretty important result. So we see here that in a series circuit, each resistor is getting the full current, but they're not getting that full voltage drop. So we see here that in series, the resistors split up the voltage. So, and then I could write this equation. So current 1 equals current 2 equals current 3 equals that total current. Like this. Or here we see that they split up the voltage. So the voltage 1 plus voltage 2 plus voltage 3 equals our total. Now, these two statements here are going to be extremely important for solving all of these. So we see that in a series circuit, each individual resistor gets the entire current, but each individual resistor has to share the voltage. And voltage goes back to 0 before it gets to the battery. That is the other very significant thing that we're going to use. We're going to see that at part G. So yeah, you're a little bit ahead of me there. But yeah, the circuit is going to automatically adjust, and it's going to be the current that automatically gets adjusted. The current adjusts in such a way that we are going to use up all 10 volts by the time we return to the battery. And it's not really magic or anything. It just has to do with if it didn't go back down to 0, that would mean we're ending up with more voltage, and we're just going to continuously increase voltage till we get to infinity. So that's just conservation of energy. We're not getting energy from nothing. All right, so we have this, and I know we've written kind of a lot. I would really suggest you kind of go through this, especially these two. I can't stress enough how important those are. All right. If you miss anything, you can always come back and watch the video later. All right, so now I found the current and voltage through each resistor. Now I want to find the power for each resistor. So that's where we have our new equation for power. So we always had our old equation for power. Power is the amount of energy used per time. But now we have our new specific formula. Power in a circuit is going to be current times voltage. And again, we derived a few other equations last class. I know power is current times voltage, but I know that voltage equals current times resistance. So if power equals current times voltage and voltage equals current times resistance, instead of voltage, I could write current times resistance equals current squared times resistance. But I can also solve this another way. I know power equals, again, I'll start with current times voltage, but I could solve this for current. Current would equal voltage divided by resistance. So I could substitute this in for current. Instead of current, I can write voltage divided by resistance times voltage equals voltage squared divided by resistance. So power also equals voltage squared divided by resistance. Now, normally I would try to make you all derive this for the test. Obviously, it's going to be open notes and everything for your test because I can't stop you. But those were our 3 power equation. So power is current times voltage. Power is current squared times resistance. Or power is voltage squared divided by resistance. So we can use any of these. The nice thing about these is I only need two of the three quantities from Ohm's law, current and voltage, current and resistance, or voltage and resistance. But we've already solved for everything here, so we can just use power is current times voltage for this problem. If you want, go through and check all these and make sure they all work. Spoiler, they do. So power is current times voltage. I want the power for each resistor. So the power used by resistor 1 equals current 1 times voltage 1. Well, every resistor in this circuit gets the full 0.01 amps of current, but 1 is only taking up 1 of those volts. So power used up by 1 is going to be 0.01 watts, or 0.01 joules per second. And, by the way, if you think about light bulbs are rated in watts. The old incandescent light bulbs were usually 60-watt light bulbs. You could also have 100-watt light bulbs. And if you look at the difference is how bright they are, right? Light is energy. So that's why light bulbs are measured in watts power. So power is another way of determining how bright a light bulb is. Newer LED lights are going to be under 10 watts. And that's just because they're more efficient at converting energy to light. But within a certain light bulb, you can still see, say it says one is 5 watts and one is 8 watts, and they're identical light bulbs. The 8-watt one is going to put out more light energy per time. All right, power 2 is current 2 times the voltage drop across 2, and power 3 is going to be current 3 times the voltage drop across 3. These all get 0.01 amps. Resistor 2 took 5 of the volts, and resistor 3 took 4 of the volts. So power 2 is going to be 0.05 watts. Power across 3 is going to be 0.04 watts. Nothing too crazy about that, just plugging in some values to the equation. All right, now F. F wants us to find the total power used by the circuit. Fairly dim. So they're not actually dim. Even like 5-watt, like a lot of times they'll write the equivalent light amount. The reason that they use less energy is that they're more efficient at converting the energy into light. So a lot of those LED light bulbs, they convert almost all of the energy into light and a little bit into heat. Incandescent light bulbs waste a whole lot of energy as heat. So they warm up the air around it instead of turning it into light. So it's not that they're dim, they just use less energy because they need less energy to create the same amount of light. If your resistors were incandescent, yeah. Oh yeah. If these were incandescent light bulbs, these would be not bright at all. I have little LED lights. I don't have any out right now, but yeah, these would be kind of the brightness of like a small LED, or like a single pixel on a TV screen would be something really small like that. Yeah, like a single Christmas light. I don't know the exact number for a single Christmas light, but they're going to be pretty small. All right, so F wants us to find total power, so I could do total power equals total current times total voltage. All right, so overall we get 0.01 amps, and we have an entirety of 10 volts. So my total power is going to be 10 times 0.1. 0.01 is 0.1 watts. How else could I have gotten total power? Power is energy per time. Energy is a scalar. Scalars we can just add up, right? They're just numbers. Like if I have a 1 kilogram mass and a 2 kilogram mass, my total is 3 kilograms. So energy and power are scalars, so I could just add up powers. So this could also be found by power 1 plus power 2 plus power 3. So I could have just added these three up. And you'll see you get the same number. And we can even test these other equations. So that total power would be current squared times resistance. So my current squared is 0.01 squared times the total resistance of 1,000 ohms. We'll still get 0.1 watts. And we can do power total. It would be total voltage squared divided by total resistance. So 10 squared divided by 1,000. And you'll also get 100 divided by 1,000 is 0.1 watts. 0.4 watts. Yeah, an LED, yeah, that makes sense for an incandescent Christmas light being about 0.4 watts. But yeah, LED ones are going to be really small. So yeah, these are right around the size of LED Christmas lights, or the power of LED Christmas lights. Which is a pretty drastic amount, especially when you consider you're using like anywhere from like 5 times less energy to 10 or more times less energy. If everyone does that, that's a pretty huge amount of energy across an entire country. All right, so a few ways we can find energy. We have 3 different equations, or we could just add up all of our powers to get our total power. Okay, so G wants us to get our total voltage, or the voltage at each point. So now this is kind of a point where we talk about the difference between voltage and voltage drop. So I can have an absolute voltage at a point, say I have 10 volts of potential at one point, or 5 volts of potential at one point. Or I could have a voltage drop. I could say the voltage goes down by 4 volts across a resistor, or the voltage goes up by 10 volts when I go across a battery. So let's draw this out one more time. Yeah, a lot lower wattage. You can also connect a lot more of them if they use lower watts, but sometimes you can't. They might still have current restrictions. All right, so I have a 10 volt battery. So this adds 10 volts. So across the battery, my change in voltage is going to be plus 10 volts. Batteries add voltage in order to push the current through the circuit. So that means when I get to this point here, I have 10 volts. But then I get to this resistor, and this is 0.1, 0.2, 0.3, and 0.4. When I go through a wire, we're assuming perfect wires. So in perfect wires, we're not losing any voltage. So all that wire is doing is perfectly moving charge from one place to another. Obviously, in the real world, wires aren't perfect, but we're going to assume they are. Then I get to this resistor. I have 10 volts. This resistor used up 1 volt, right? Resistor 1 used up 1 volt. So my drop in voltage across resistor 1 is minus 1 volt. I lose 1 volt. So that means if I had 10 volts and I lose 1 volt, I'm down to 9 volts right here. Yeah, 4 is going to end up at 0 volts, yes. And then I get to resistor 2. The voltage drop across 2 is 5 volts. So I lose 5 volts. So I had 9 volts. I lost 5 volts, so I'm down to 4 volts. And then my voltage drop across 3 is 4 volts. So I lose 4 volts here. I had 4 volts, I lose 4 volts, so I'm down to 0 volts. And then just like that, I'm back down to 0, I'm back down to my ground state before I add more voltage back here. And again, there's nothing magical about this. It's just conservation of energy. It's saying that I'm not consistently getting more and more voltage. If this, say, didn't go down to 0, then I would end up above 10 here, and it would just constantly be increasing in voltage, and I would go to an infinite amount of energy, which can't happen. The other way would be imagining that I ended up lower. Let's say I went down to -1, which this can kind of happen in a sense, but what's really happening there is as your battery is losing up voltage, then as it uses up energy, it's going to put out less voltage. So it's not going to be this going to -1. It would just say as this battery goes on, let's say it is only putting out 9 volts after a while, then all of a sudden it would only put this to 9 volts, and then that would still go down to 0. So it can't end up above 0 because that would mean I'm adding an infinite amount of energy over time, or at least over an infinite amount of time. And it can't go back less than that because what's going to happen is this will just be 0 and it'll put out less voltage. And these are going to take up less voltage in a way to send that back to 0. All right, so I know the voltage at point 1 is 10 volts. The voltage at 2 was down to 9 volts. The voltage at 3 was down to 4 volts. And then the voltage when I return to the battery is 0 volts. I've used up all of that potential. All right, H. Yeah, we're definitely going to have to do some of this next class. That's all right. We're not in a hurry. I'm trying to go through this more thoroughly than anything. Yeah, it's bad to touch both ends of the battery. So what ends up happening is if you touch both ends of the battery, you just have wire to wire. What happens is the wire has a really low resistance. So if you have a low resistance, you get a really high current. And if you get a really high current, you have a really high power. Power, most of the energy is going into heat. So that means you have a really high current, really high power, really high heat output. So things get really hot and you can start fires, or the battery itself could burst once it gets too hot. So yeah, don't short out batteries. Like with your fingers? Well, no. If you touch both ends with your fingers, your body itself has a pretty high resistance. So you would have to touch a really high voltage battery in order to get enough current to actually hurt you. So yeah, you can touch both ends of a small battery just fine. You can touch both ends of even a car battery. Yeah, in AA you should be fine. But when you start getting higher voltage, like 120 volts from the wall, you definitely don't want to be touching that. That can send enough current to harm you. But yeah, AA battery is just 1.5 volts. That's not going to do anything to you. It will technically send a current through you, though, a non-zero current. All right, so H, the 400 ohm resistor is removed from the circuit. So I have a 10 volt battery. This one is my 100 ohm resistor. This is my 500 ohm resistor. And then I remove my 400 ohm resistor here. So what do we call this circuit when it's not complete? It's called an open circuit. And this is one of the main disadvantages of a series circuit. So let's say I connect these two light bulbs. So if I connect this one here, and I connect this here, we see we get a fairly bright light. So when I connect this one here, and then I'll put this in here, come on, go in there. And then I connect this one here and this one here. Now I get a circuit. So we see immediately one of the disadvantages is, let's turn this off. You can barely see this one lighting up. You can't see this one lighting up in the video, but it actually is definitely lighting up. You just can't see it. You're going to have to trust me on that. So that's one of the disadvantages, how we saw that these were having to share the voltage. And because they have to split up the voltage between them, they're not so bright. So the more I add in series, the more and more dim these get, right? It's a whole grocery store thing. It has to go through this grocery store line and this grocery store line. So it's really hard for the current to get through. So we have low currents, low voltages for each of these are splitting it up, and we get really low powers and they don't shine very brightly. The other big advantage is, let's say this bulb burns out or I remove that light bulb. What happened to this light bulb when I removed it? So I removed this other light bulb, and this light bulb turned off. Yeah, it just said chow and dipped. It just went away. It's no longer on. So if I remove one of these, the other one turns off. That's a pretty severe disadvantage. If I remove this resistor, it turns into an open circuit, and then all of a sudden, no current flows. No current at all. So the second this is open, no current at all. So the other resistors get no current anymore. So the current through resistor 1 equals the current through resistor 2. It's just completely 0 amps. So an advantage of this series circuit is it's simple. It's really easy to make. I just go through each individual one. But the disadvantage is if I take this one of those away, none of them work. So yeah, that's like older Christmas lights work exactly like this, where a single light burns out and they all stop working. And that is an absolute mess because you have to go through and try to figure out which one is actually burned out. And that can take a really long time. So a few disadvantages. One bulb burns out, they all turn off. And as I add more and more, they get more dim as they're having to share more and more voltage, and they get higher and higher resistance, less and less current. It gets harder and harder to light them up. All right, so now if I add more resistors, so say we have here, we have this resistor, this resistor, this resistor, and let's say we add in a resistor 4. So we're at a grocery store. We go through one line, the second line, the third line, and then an employee walks up to us and says we have to also go through a fourth line. How upset would you be? I would be pretty upset, because that would mean I am going to spend more time. It is now going to be harder to leave the stores. So as I add more and more resistors, I get more resistance. More resistors in series means more total resistance. You'd be shoplifting. That, again, is a short circuit. We'll get to that later. So yeah, so more resistors in series. I have to go through 3, 1, 2, and 3. Now I have to go through a fourth, and it's really hard to leave. More total resistance, more hassle to get out of the store. And then I know my voltage equals current times resistance. Now, I didn't change anything about my battery. I still have a 10-volt battery here, so that didn't change. My resistance gets higher. So as my resistance goes up, in order to keep the same voltage, that means I get less current Or another way of looking at that, current would be like the people in the store, how many people are getting through the line. When it's just having to go through 3 lines, a certain amount of people will get through. But the second I add a 4th line everyone has to go through, it's going to get harder for people to leave the store. And that line is going to get more and more backed up, and we're going to have fewer people getting through the store. So we have less current. So more resistors in series, more resistors in series means less current. Yeah, Walmart on Black Friday, but just so that would be a really high current. And so we see here when I just have the single light bulb, it's pretty bright. Whenever I add a second light bulb, things get pretty dim where you can barely see it. And I can even go and add a 3rd light bulb to this. So when I add this, you might not even be able to see these light up. So when I add this 3rd light bulb in here, yeah, you can't even see it. You're just gonna have to trust me that this one is lit up. These 2 are receiving so little current that they're not lit up at all. But this one is just the tiniest amount lit up. Actually, yeah, you still can't see it. But that little one there is just barely lighting up. So as I add more and more of these, it gets harder and harder for the current to go through, and it gets less and less current, more and more resistance, and harder. Yeah, you could barely see it for a second there. The other ones just weren't lighting up at all. All right. That was the second question. Now, yeah, little tiny pale yellow dot at the center. Now let's look at the third one. This is the last one we'll go through today. So this previous one, we're adding things in series. We just keep adding them. It goes directly from one onto the next. This next one we're going to be talking about is going to be series. This is a little bit more complicated of a circuit. So this is parallel. I think I just said series. We're looking at a parallel circuit now. So a parallel circuit, instead of having to go through each individual spot, this is going to be like a normal grocery store. So I have a 9-volt battery here. I go out this way. I can go through line 1, or I can go through line 2, or I can go through line 3. Now, compared to that first horrible grocery store, now I have 3 possible choices. I can go through 1 or 2 or 3 instead of 1 and 2 and 3. So this one, what do you think my resistance is going to be? Is it going to be easy or hard to leave this store? Yeah, someone outside just honked. Yeah, I don't know what's going on over there. So yeah, so this is going to be a lot easier. I could go through this or this or this. This is going to be easy to leave the store. So we're going to expect some low resistances. I don't think it's Morse code. I think they're just annoyed that the person isn't walking outside. I think my favorite story was there was like a person in Canada, and like their neighbor would get picked up every morning, and their neighbor would drive up in their driveway, or the person picking up their neighbor would drive in their driveway and just honk on the horn continuously at like 6 a.m. And they kept telling them, "Hey, stop doing this. This is my driveway." So they put their garbage bin out there so they couldn't drive in, and then they just drove and then slammed into the garbage bin and like hit it to the side. And they wouldn't stop doing it, so the person got fed up and like filled the garbage bin with water. And it being Canada in the winter, no, they did not say sorry. They were completely unapologetic, but they filled it up with water in Canada in the winter, and it completely froze over. So they went to like drive and like slam into the garbage can, and it was a solid brick of ice, and they completely wrecked their car. Yeah, that's kind of funny. Can't really do that in Texas, though. But yeah, so trying to find our total resistance. So for a parallel circuit, this we have a really kind of weird looking equation. I'm not going to go into why this works. I could derive it after this if you really want to know, but we're not going to worry so much about that. But we see this total 1 over total resistance is 1 over resistance 1 plus 1 over resistance 2 plus 1 over resistance 3 plus all of the rest. Steel posted mailboxes. Yeah, they're hard to drive over. So this equation is going to be easy to mess up for a few reasons. 1 over total resistance. Well, resistor 1 is 90 ohms. So 1 over 90 plus 1 over resistor 2 is 45 ohms plus 1 over resistor 3 is 180 ohms. Now, when I add these all up, this is obviously 1 over 180 plus 1 over 90 is 1 over 270. Well, 2 over 270. And I can just add up the tops. This is just 3 over 270 plus 45 is 315, right? This is 3 over 315, correct? I do not believe so. That is not how you add fractions, right? We would have to sit here and get a common denominator. The lowest common denominator would be 180. So we'd have 2 1/80ths plus 4 1/80ths plus 1. So we'd have like 2 plus 4 plus 1. We have 7 1/80ths. Or we have these things called calculators that do fractions for us. And then I'm even lazier. I just do 90 to the negative 1 plus 45 to the negative 1 plus 180 to the negative 1. All right, so we get 0.03889, something around there. So that's my total resistance, correct? No. This is equal to the inverse of total resistance, 1 over the total resistance. So I'm going to have to flip both of these over. Yeah, it's 1 over that. So how I flip things is by doing them all to the negative 1, right? So I could do this all to the negative first power, negative first power, negative first power, or 1 divided by it would also work. So that total resistance is going to be 1 over 0.03889, whatever, do that as many times as possible. So my total resistance here is going to be 25.71 ohms. I mean, if you prefer, it's 1/87ths. I actually didn't round. If you look at my calculator, I just used the I actually deleted it, but I just used the previous step. So honestly, how I normally put this in my calculator, it would be 90 to the negative 1. Notice a parenthesis at the front, plus 45 to the negative 1, plus 180 to the negative 1, and then I just do negative 1. So I normally just do this all in one step. All right, now we notice this was a 90 ohm resistor, 45 ohm, 180 ohm, but this is 25.7 ohms. So my total resistance is less than the resistance of the smallest resistor. So for a parallel circuit, my total resistance is less than the smallest resistor. In series, we saw our total resistance was bigger than the biggest resistor. And this kind of makes sense, right? Because I could go through this one or this one or this one. Resistor 2 is my smallest at 45 ohms. So back to the grocery store. This is the best person to get you checked out and get you to the car faster. But let's say they open up either of these, just the fact that they have other aisles, even if these people aren't as good at scanning your groceries quickly, just the fact that they exist help you get through the circuit. So you could go through the really good person, or you have two other okay people to check out your groceries. But just the fact that I have three paths to get through makes it easier to get through. So it's easier than everyone trying to go through this one. They could go through this one or these other two. So my total resistance gets smaller and smaller. As I keep adding these, I get less and less resistance. All right, so B wants us to get the total current through the circuit. So that's just going back to Ohm's law. So total voltage equals total current times total resistance. Or total current is going to be divide resistance over. So total voltage divided by total resistance. So I have 9 volts, a total resistance of 25.71 ohms. So my total current is going to be 9 divided by 25.71. 0.350 amps. Yeah, 4 times worse than the one in the middle. But they still make it easier to leave, even if they only check out one person and the time it takes for the other person to check out 4 people, that's still getting 5 people out in the same amount of time that the other person could only get 4 people out. So even adding in a person with a really high resistance in parallel, even that is making it easier overall for people to leave the store. Makes it easier overall for current to flow, makes our resistance smaller. All right, so C says find the voltage at points 1, 2, 3, and 4, and 5, 6, 7, 8. So I'm going to write that up here. 1, 2, 3, 4, 5, 6, 7, 8. Now, again, like this previous part, we're only going to lose voltage if we go through a resistor. So here, I've just gone through the battery, so I'm at 9 volts. Are there any resistors on this top part right here? No resistors at all. So if there's no resistors, just these perfect magical wires without resistance, that means my voltage isn't dropping across this top. So this whole area up here is connected to the battery at 9 volts. When I get back to my battery, I'm going to have 0 volts. But there's no resistors in here, so that means I'm going to have 0 volts along this entire bottom. That's really straightforward, isn't it? I have 9 volts all the way up here, 0 volts all the way up here. I'm in the store here, haven't gone through any checkout lines, out of the store here, ready to go to my car. So the voltage at point 1 equals a voltage at point 2 equals a voltage at point 3 equals a voltage at point 4 is 9 volts. And then the voltage at 5 equals a voltage at 6. That is not a 6. Equals a voltage at 7 equals a voltage at 8 is all 0 volts. So that sets up our voltage drops pretty easily. So D wants us to get the voltage drop across each resistor. Well, resistor 1, I go from 9 to 0 volts. So my voltage drop across 1 is 9 volts. 2, I go from 9 to 0 volts. So the voltage drop across 2, 9 volts. 3, I go from 9 volts to 0 volts. So the voltage drop across 3 is 9 volts. That seems pretty significant. Each one of these resistors is getting that full 9 volts of voltage. So they're not having to share voltage at all. If we remember back to our series circuit, we were having to share the voltage. So here we see in parallel, each resistor gets the full voltage. Or I could write the voltage drop for resistor 1 equals a voltage drop for resistor 2 equals a voltage drop for resistor 3 equals our total voltage. So they're not having to share that at all. Well, we'll see. There's some aspects that might not be as good. So in series, they had to share the voltage. But in series, they all got the entire current from the battery. They all got the entire current from the circuit. So let's see what happens here for an entire circuit or for each individual resistor when we're talking about current. Like finding resistance total. Not quite. So we already have the voltage for each one of these, and we know the resistance. Well, I know voltage equals current times resistance, so current equals voltage divided by resistance. In a sense, it is like this. This is what we use to calculate that equation. If you want me to derive that later, not right now. I don't have time for that without making the video too long. It's already gone long as it is. So current equals voltage divided by resistance. So current 1 equals voltage 1 divided by resistance. Current 2 equals voltage 2 divided by resistance 2. And current 3 equals voltage 3 divided by resistance 3. So all of these get 9 volts, and resistor 1 is 90 ohms. They all get the full 9 volts, and resistor 2 is 45 ohms. They all get that 9 volts, and resistor 3 is 180 ohms. Nine divided by 90 should just be 0.1 amps. Nine divided by 45 should just be twice as much, 0.2 amps. And then 9 divided by 180 is 0.05 amps. Which kind of matches what we expect. Cashier 2 had the smallest resistance, so we expect the most people going through, the most current going through. 3 had a real high resistance, 180 compared to 45. So they're the hardest line to get through. They're the worst at checking out the groceries, so fewer people go through. And in fact, they have 4 times as much resistance, so they have 1/4 as much current. 1/4 as many people go through that line. Now, in series, all the resistors got the full current. But in parallel, they're each getting a little bit different current. But what do these add up to? 0.1 plus 0.2 plus 0.05 equals 0.35. Look at that. So in parallel, the resistors split up the current. So we're going to see current through 1 plus current through 2 plus current through 3 is going to equal our total current. So again, this is big. These are the big things right here. So let's put these all in the same thing. So we see in a series circuit, they all get the full current. The current has no choice but to go through here, then to here, then to here, then to here. In parallel, the current goes out and it gets to a point here, it can choose to go right or down. It has to choose. Some electrons go through here, some electrons go here. Then I get to this point, they have another choice. They can go either way. And then the rest go through here. So electrons, they're a single electron. They can only go through one path, ignoring quantum mechanics. They can only go through one path. So they have to choose. Some electrons go through 1, some electrons go through 2, some electrons go through 3. So the current itself splits up. They make a choice. So series, all the circuits go through every resistor. Each resistor gets the entire current, the total current. But in parallel, the paths split, so the current splits up. So the sum of the currents equal my total. So they have to share all of those currents. In series, you go through each resistor individually, and so they're going to split up that voltage. 1 uses up some of the voltage, 2 uses up some of the voltage, 3 uses up some of the voltage. So they're having to split up and share the voltage to where if I add these up, I get my total voltage. But in parallel, because each one is connected just by wire to the battery, this has its own little connection to the battery. This one has its own connection to the battery. This has its own connection to the battery. Each one of the resistors in parallel is getting the entire voltage from that battery. So the total voltage provided to the circuit is all getting to 1, all is getting to 2, and all is getting to 3. So these 4 rules, these are the key to solving every single circuit problem with just resistors. So the 4 things I have in stars here. Write this down. If you're watching the video later, pause, write that down. This is going to be the thing you need to use for all of these. So far, so good. Is it okay how we got there? I know this has been a lot of information. There's a lot to keep straight here. And we'll go through this again next class. I'll have another problem that we'll do where we'll use these concepts again. All right, F wants us to find the power used for each resistor. So that's, again, back to something relatively straightforward. Power is just current times voltage. All right, so they all get 9 volts, but one only gets 0.1 amp times 9 volts. Resistor 2 gets 0.2 amps and the entire 9 volts from the battery. And then resistor 3 only gets 0.05 amps, but it still gets the entire battery voltage of 9 volts. .1 times 9, 0.9 watts. 0.2 times 9 is 1.8 watts. 0.05 times 9 is going to be 0.45 watts. And we could go through and get the total power for the circuit. So total power would be total current times total voltage. So 0.35 times 9 volts. Not off the top of my head. 9 times 0.35. We get a total power of 3.15 watts, which we'll see is the same as just adding these up. So this is going to be identical to just power 1 plus power 2 plus power 3. So powers, you're always just adding them up. That is way more power than series, yes. So that is an advantage. One advantage of parallel is we get smaller resistances, so we get bigger currents. Those bigger currents allow us to get bigger powers, but that can also be a disadvantage, right? Power, a lot of that energy is lost to heat. If you get too much current and too much power, you actually start getting into risks of starting fires and burning things down or overheating components. So that's one of the yeah, big boom time. This is why you shouldn't plug all of everything in your house is mostly connected in parallel. If you keep plugging things into extension cords and then you plug extension cords into extension cords, then that's happening. You're putting more and more things in parallel. You're adding more checkout lines. It gets easier and easier for the current to flow through the entire circuit as your resistance goes down. You get bigger and bigger currents, you get bigger and bigger powers, and then your electrical outlet catches fire. But hopefully before that, you trip a circuit breaker in your house. Those are rated to stop your current, and that's what's happening. You're lowering your resistance. You're drawing more and more current. As you draw more and more current, it gets to a point where the breaker trips, and it says, no, you're going to burn your house down, and I don't want you to burn your house down. Well, I guess it doesn't say that, but... All right, so G... I remove one of our light bulbs. So same thing, G and H, we do the same thing. So I have a battery here. I go here. I remove the 45 ohm resistor. So the person who is really good at checking people out goes away. So if I reduce the number of checkout lines, is it getting easier or harder to leave? Yeah, don't burn other people's houses down. It gets harder to leave. I closed out a checkout line. It's harder to leave my store, so my total resistance is going to go up. Right? I had 3 lines I could go through. They closed one of the checkout lines, and it got harder to leave. And if I remove another one, then it would get even harder to leave. And if I remove the last one, it would get impossible to leave. So our total resistance is going to go up as we remove resistors in parallel. As we remove parallel resistors. Or they could go and add another checkout line. Let's say they go and they add another checkout line, then it gets easier, right? They open a third line. Like this would be, imagine you go to Walmart and every single one of the checkout lines is open. That would be a very low resistance. It would be really easy to leave. But in reality, you go to a Walmart and they have like 2 checkout lines open. It gets harder and harder to leave as they have fewer and fewer parallel lines open. Arson is not fun. Do not burn down people's property. H, if one of the light bulbs is removed, will the other light bulb stay on or not? So here I removed a light bulb. Are these other ones staying on? Yeah, there's still a complete path for current flow. We still have a closed circuit. Which means the light bulbs stay on. I cannot write right now. Light bulbs stay on. And by the way, I actually already solved I over here. Whoops. So let's set this up in parallel. So I have this one. Let's put you here. Actually, no, you weren't the one I was putting there. These are the ones I was putting there. All right, so I have one light bulb here. So if I put it in parallel, I want to connect it directly to the battery. So that would be directly to right here, directly to right here. So I plug two of these in, and they're still really bright. I could go and I could add a third one in, and they're all going to stay equally bright. So I keep adding these in parallel, and they're staying the same amount of brightness, right? So this is a really nice thing about parallel. I can keep adding, I can keep adding. What's happening is the total resistance of the circuit goes down as I keep adding things in parallel. As I get lower resistances, I get bigger currents. So all of these are having to share the current, but because the overall current goes up, they don't have to end up sharing more. So let's add more, or let's actually plug you in. All right, so I have these three in here. I can remove one, that light bulb goes out, the other light bulb stay on. That's really nice. I can remove this one, and the other two stay on. That's really nice. Or I could remove this one, and that stays on. So these are more modern Christmas lights, where if one light bulb burns out, all the other ones stay lit. Or everything in your house. If you say turn off a light, it doesn't turn off your computer also. If you unplug your toaster, it doesn't turn the fridge off. They each have a complete path back to the circuit. So as I go, and if you even notice, as I put more of these in, the brightness of this bulb is not changing. Right? So that's another really interesting result about all of this, is that we can look to our equation for power. Let's go to the power is voltage squared over resistance. Well, no matter what, these are all getting that full, for this one, 1.5 volts. So that's not changing. Resistance of the resistors aren't changing. So let's say power for resistor 1 equals voltage 1 over resistance. If I plug in a second resistor, if I plug in a second light bulb, so looking at this, so whenever I have this, I have a certain voltage and resistance. So then I plug in voltage. I plug in bulb 2. Well, the voltage 1 was unchanged. It's still getting the full 1.5 volts. It's still fully connected to the battery. The resistance of resistor 1 didn't change. My total resistance did, but the resistance for this light bulb didn't change. That's intrinsic to the light bulb. So I didn't change voltage, I didn't change resistance. So that means power for that light bulb is unchanged. And that means the brightness is unaffected. So that's why you can keep plugging things in. When you turn on other things, your light in the ceiling doesn't dim. Make life support, yeah, I mean, it actually is, you say that, but yeah, it's definitely, life support is definitely on a parallel circuit. Everything is that's connected in your house. Very few things in your house are actually connected on a series circuit. So series circuits are generally a lot nicer in the real world. The math is a little bit more complicated, but so that's a little bit different. That deals with like startup currents and things like that. When you directly start up something, your vacuum cleaner draws like 5 times more current than it normally does. And that's a little bit different because you're suddenly drawing more than the circuit can provide, and then things dim, and then it goes back to normal. So that's a much more complicated interaction actually going on there that deals with alternating current circuits, which are more difficult than what we're doing on here. It deals with something called inductance, which, if you want to talk about that, go into Physics C. All right, so that's a really nice thing. I can keep adding these things in parallel, and the brightness is completely unaffected. So we'll stop this here. We still have some left over on this, and we'll go through this next class. Be working on your homework. We've covered enough to talk about the homework. If you have questions on the homework, you can ask them next class. In fact, I'm hoping for questions on the homework next class because there is quite a bit going on with this. Again, if you didn't already get those down, these 4 things boxed in red with the stars are the important things to look at. These are going to be the most helpful for your homework. All right, so this has already gone on for about 1 hour and 20 minutes. Sorry, this has been a longer video, but there's just quite a bit more to go through for these two. Again, finish things like mostly your quizzes and labs, get those in. Other than that, we're just going to keep going through this. Finish up with simple circuits. This week, we'll go into more complicated combinations of series and parallel next week. Then you'll get a test review and a test in about 2 weeks. So just keep working. Show up to tutoring for questions, show up to class next class. Otherwise, have a good day and the rest of the week.